Last time we met, we found the population mean. We talked about that. We found a population standard deviation and also the distinction between the sample standard deviation. And we found those items given a frequency distribution, right? So we had to find the midpoint, and then we had to use a calculator. We used that one variable statistic, right? And we were able to find the mean and the standard deviation. On the handout, on this set of lecture notes, so I'm going to go back into the course momentarily. Okay, so we talked about finding the deviations and the means from a frequency distribution. If you follow that slide, there's something called an empirical rule. But before I discuss the empirical rule, I just want to backtrack for a second and I want to talk about a stem and leaf plot. All right, so that's just a stem and leaf plot. Okay, we talked about a box plot. We talked about a makeup of a box plot. And a box plot is just one way to physically express a data set. Another way to physically express a data set is through something called a stem and a leaf plot. So I'm taking this list of numbers, and this list of numbers, it actually comes from, okay, just to show where I'm getting this stuff from, in module 1, part 2, the handout. All right, we use this data set, and we found the mean, the median, the mode, and the standard deviation. I'm going to use the same exact data set, right? 27, 22, 20, 32, 34, 29, 25, and 34. I'm going to use that to construct what's called a stem and a leaf plot. So in a stem and leaf plot, you have a stem. I'm going to separate this out in columns. And then you also have what's called the leaf. Now, when you're asked to construct the stem and a leaf plot, they'll give what's called a legend. And what a legend is it tells you what your stem is. Now, our stem, just notice that these numbers range from the 20s to the 30s. Our stem is going to represent the first digit of our number. The leaf represents the other number. So all together, we're going to represent a number, but it's going to be in twos. We're going to have a stem part and a leaf part. So, for example, I'm going to put all of these numbers in, I don't necessarily have to put them in order, right? So constructing this stem and leaf plot, my first stem is going to be 2. So what that means is all of the numbers whose first digit is 2, they're going to go along this row. And the leaf is going to be the second digit of that number, right? So I'm going to kind of put these in order. So we have a 20. So notice the stem is 2 and my leaf is 0. I'm just going to cross that out. We have, I believe next is 22. So notice my stem is 2. My leaf is going to be 2. So that represents 22. The next number in order, I believe, is going to be 25. So notice my stem is 2 and my leaf is 5 in that number 25. And our next number that is in the 20s is 27. So my stem is 2, my leaf is 7. So as you can see on this first row, this actually represents 4 numbers. It represents 20, 22, 25, and 27. Now I'm going to just move up to my next stem, which is 3. Oh, I'm missing one? Okay, 29. I'm sorry. 29. All right. So just going back, this would actually represent 5 numbers. 20, 22, 25, 27, and 29. So for the next row, I'm going to use the next stem, right, which are the numbers in the 30s. So the first number, I believe in order, is 32. So my stem is 3, my leaf is 2. So that represents 32. And then I have 34 once and 34 twice. Bless you. All right, so this is what a stem and a leaf plot looks like. So if you see that in the homework, if they ask you to construct the stem and a leaf plot, they'll give you some indication on what your stem is. It's either going to be the first number or the first 2 numbers according to how many digits you're dealing with. And again, it's just a physical way to represent data. All right, now as we look at these physical ways to represent data, we're going to talk about something called skewness of distributions. All right, and before we actually talk about skewness, I just want to point out the fact that skewness lies in the tail. Okay, so I'm going to talk about what that means in a second. So if it asks you if a graph is left skew or if a graph is right skew, the skewness lies in the tail. So if you're looking at your plot, if your distribution has a tail to the left, it's left skew. If it has a tail to the right, it's a right skew. We also have what are called uniform distributions, which we don't use in this course. And then we also have the normal curve or the bell curve. Okay, so here's some examples. So if the graph of your distribution looks something like this, since the tail is in the left, this is actually a left skew distribution. In the next diagram, notice this diagram has a tail to the right. This would be considered a right skew distribution. And then we have a distribution that is symmetric. So it doesn't have a right tail. It doesn't have a left tail. This is called a normal distribution. And as we go further along in the class, we don't deal with the left skew or the right skew as much, not in this course, but we definitely deal with this normal distribution. It could also be called a bell curve, because it kind of has a Taco Bell shape, but they changed up their logo. It could also be called a normal distribution, or you may even see the word normally distributed. So if you see any one of these words, normal distribution, bell curve, normally distributed, it follows this bell-shaped curve. When we're dealing with this bell-shaped curve, and now I'm going to go back to our slides, back to the lecture notes. Where is it hiding? We have something called the empirical rule. This empirical rule only applies to the bell-shaped curve, not to the left skew and not to the right skew. All right? It only applies to the bell-shaped curve. And here's the empirical rule. It's sometimes called a 68, 95, 99.7 rule. And here's what that means. If you look at your curve, and at the bottom of the curve, we have two values that you are going to know. You're going to know the mean. So in this bell-shaped curve, the mean is in exact center of the curve. So notice that X bar, right, that represents the mean. S is the standard deviation. The 68% and the 68, 95, 99.7, it says that 68% of the data is within one standard deviation of the mean. That means it can be one standard deviation above or one standard deviation below. So notice that this chart gives you percentages. From the mean to one standard deviation above, it gives you 34%. From the mean to one standard deviation below, it also gives you 34%. But notice the rule states that it's 68% falls within one standard deviation. So that either could be one standard deviation below or one standard deviation above. Right? So notice that 34 plus 34 is where the 68 comes in. 95% of the data is within two standard deviations of the mean. So if we look at this particular point here, that's X bar minus 2 times S. So X bar is the mean, S is the standard deviation. So if you put in your mean and your standard deviation, that would give you the value for two standard deviations below the mean. And if we take a look at the top and go down, right, 95%, this will be two standard deviations above the mean. So notice how all of the percentages are listed out on this particular empirical rule. And then 99.7 says that 99.7% of the data are within three standard deviations of the mean. Now, when we start talking about, okay, because this is actually like area, right? 68% fall within one standard deviations of the mean. This is area. And from what we're going to deal with from this point going forward, area is probability. So in a lot of the questions, they're going to ask you to find the probability of this happening or find the probability of that happening, as we want to see in just a second. The area you get is a probability that something can happen. So area is probability. All right, now we're going to relate this to a problem. My stuff is all over the place. So here's that empirical rule once again, 68, 95, 99.7. Okay, over to the side, I'm just going to write out the fact that area is probability. So now how will this look in an actual problem? Okay, on the handout, this is problem number 5. Okay, and I'm going to slide this up. Now, this empirical rule, this chart, you can use this on a test. You can use this on a final exam, anything we do in class. This chart is very helpful when finding the area or probability. So here's an example, number 5. It says the Acme company manufactures widgets. The distribution of widget weights is bell-shaped, right? So it's going to follow that bell-shaped curve. The widget weights have a mean of 51 ounces. So X bar is equal to 51. And it has a standard deviation of 10. So S is going to equal to 10. Use the empirical rule to answer the following. So anytime you're asked to use the empirical rule, I would pull out this diagram, right? So I'm actually going to write along with it on problem number 5 so we can actually see these probabilities. All right. So before I even begin the problem, I'm going to write out the numbers that should lie on the bottom of this bell-shaped curve. So we're given that the mean is 51, the standard deviation is 10. On your bell-shaped curve, the mean is always located in the center. So for X underneath X bar, I'm just going to write 51, right? That's going to give me a value for X bar. If I go one standard deviation above the mean, what's X bar plus S? 61, right? Because X bar is 51, the standard deviation is 10. So this is 61. So if I go 2 standard deviations above, this number should be what? 71, right? Because X bar plus 2 times S. Or remember, for the other operations, you got to multiply before you can add. So 2 times 10 is 20, and then 20 plus 51 is 71. And then 3 standard deviations above the mean should be what? 81. So it's just like I'm adding 10. Now let's look at the standard deviation below the mean. So what should be my value here? X bar minus S should be what? 41. And then notice that these numbers to the left of your mean, they're never negative. So 2 standard deviations below the mean should be what? 31, and then 3 standard deviations below the mean should be 21. Any questions on where the bottom axis comes from? It comes from knowing the mean and the standard deviation. Now we're going to answer these questions. A says 95% of the widgets lie between what 2 numbers? 31. So if I look at my empirical rule, this is that 95%. So it's 31 and 71. B says what percentage, or some of these problems may read, what is the probability of the weight if it lies between 51 and 61 ounces? Well, if I look back at my empirical rule, between 51 and 61, how much of the data lies between those two? Should be 34%.
Because the line is symmetric, right?
That's right. Well, that's because we only want this area between 51 and 61. All right. And then lastly, what percentage of widget weights lie between 21 and 81? 99.7. So that's 99.7%. All right, any questions about number 5? Whenever you're asked to use the empirical rule, I would pull out this little empirical rule slide and I would literally write the numbers down just as we did. And you can use the empirical rule to like pull out these percentages or probabilities. All right, so that's using empirical rule. Okay. For number 6, well, I guess before we go to number 6, I want to just go back to this empirical rule for just a second. I want to erase that. We do have something called we have what's called the normal curve, which is what you see here. We also have what's called a standard normal curve. In a standard normal curve, the mean is 0 and the standard deviation is 1. And this is for a standard normal curve. And if you're dealing with a standard normal curve, you have what are called z-scores. So the standard normal curve and z-scores. Okay, so what is a z-score? Well, a z-score, just like the numbers when we put in 51, 61, the only difference about a z-score is that a z-score ranges between -3 and +3. So now we just saw if something is below the mean, that doesn't mean it's negative. Okay, that just means it's one standard deviation is below 2 or either 3. However, when we write out our standard normal curve, if the mean is 0, so notice my normal curve is centered at 0. So one standard deviation above the mean would just be 1. 2 standard deviations above the mean would be 2. And then 3 standard deviations above the mean would be 3. If I go below my mean, 1 standard deviation below my mean is going to give me a what? So if I take 0 minus 1, I'm going to get a -1. 2 standard deviations below the mean is a -2, and 3 standard deviations below the mean is a -3. These are called z-scores. And they only call a z-score if they're between -3 and +3. So what we were doing earlier in question number 5, we actually had values, 51, 61. Those things are not z-scores. A z-score has to be between -3 and +3. So what we can do is we can take a z-score, and if you know the mean and the standard deviation, you can convert that to what's called a raw value, like what we were dealing with earlier, 51, 61, and so on. And then you could also take a raw score value and convert it to a z-score, right? And it would be reduced to a number between -3 and +3. So when you see the word z-score, they're referring to a standard normal distribution that has a mean of 0 and a standard deviation of 1. Okay. And it's called standard normal because a mean of 0 and a standard deviation of 1 will standardize your curve. So your baseline will fall between -3 and +3. All right, so let's look at an example. It says a normal distribution So you're going to notice when the problem says a normal distribution, they're talking about that empirical rule, and they're talking about z-scores. So a normal distribution has a mean of 127, a standard deviation of 9. Find the z-score. So remember that z-score is the -3 to +3 value for a data value of 137. All right. So if I go back to the slides, there is a z-score formula. So it says a z-score, or standardized value, right, the -3 to +3, is a number of standard deviations that's supposed to be that a given value x is above or below the mean. It is formed by using the following expression: z, which represents z-score, that's equal to x, and x would be your data value, minus the mean. So your mean is x bar divided by the standard deviation. So I'm going to go back to the notes. So this is the z-score formula. Z is equal to x minus x bar divided by S. You may see it written this way or written with the population parameters. Right? So just to make that distinction, what you actually see on the slide, remember that mu and this sigma, those are population parameters. And what I have here are x bar and S, which are the statistics. Okay? So you might see that written either way. All right, but since we're dealing with x bar and S, in the form I'm just going to use x bar and S. So x is the data value, okay, where x is the data value, x bar is the mean, and S equals to the standard deviation. So what I'm going to do is I'm just going to substitute. So x from our problem, that's going to equal to 137 because it says find the z-score for a data value of 137. Minus, that minus is a part of our formula, minus the mean, which is 127, divided by the standard deviation, which is 9. All right, so I'm using the z-score formula. So remember that x is your data value, and they give us an x value of 137. The mean is 127, and the standard deviation is 9. Right, so all of that was plugged and chugged into the formula. And now we're going to simplify the numerator. So 137 minus 127 is 10 over 9. And I believe if we divide 10 by 9, we should get 1.1, I believe. All right, so we get 1.1. So that means a data value of 137 has a z-score of 1.1. Right.
It says round 2 decimal places. So
Oh, I'm sorry, 1.11. Yeah, round to 2 decimal places. You can also use this z-score formula. I believe I should give you that one. To find x. So this is that first formula. Z is equal to x minus x bar divided by s. And this would, I don't know what's going on. This will be the z-score formula to find x. Okay, because sometimes you may be given the z-score value, you'll be given the x bar value, you'll be given s, so you may have to use this formula. So x is equal to s times z plus x bar. All right, so I'm going to give an example of that. So what I basically did was I took this formula and solved it for x. So I multiplied both sides by s, and then I added x bar to both sides. So we'll give an example. So here's an example. Find the data value for a z-score of 2 if the mean is 51 and the standard deviation is 10. So it says find a data value for a z-score of 2 if the mean is 51 and the standard deviation is 10. All right, so we actually have this. I'm just trying to relate it to this thing. So now if I look at the chart, well, let me just go back. I forgot we changed this up. But up here, let's just say if I go back, this should be in your notes. X bar was 51, and then S is 10. So that no longer makes this like a normal curve, a standard normal curve. So we have 51, 61, 71, 81. And then if we go below the mean, this was 41, 31, 21. And underneath, I'm just going to dovetail out the z-score. So that's 0, 1, 2, 3. That's -1, -2, -3. So now just by looking at this, which number has a z-score of 2? Should be 71, right? Because we kind of mapped everything out. So going back to this problem, it says find a data value for a z-score of 2 if the mean is 51 and the standard deviation is 10. We kind of mapped that out, right? And we know it should be 71. But here's the mathematical way to do it. Let's just say you didn't have that empirical rule, nothing was mapped out. You could use this formula. X, right? Because X represents the data value. That's equal to S times the z-score plus X bar. S is equal to 10. Z is equal to 2, and X bar is equal to 51, right? So now if I plug all this stuff into the formula, S is 10, Z is 2, plus X bar, which is what? 51. And now if we simplify, so just remember, no matter what math class you're in, you're always using order operations. Please excuse my D.R. Sally. So you must multiply before you can add anything, right? So first thing I'm going to do is add 10 times 2, which is 20. And now if I simplify, 20 plus 51 should equal to 71. So 71 has a z-score of 2. All right. So you may want to write this formula down somewhere. Okay, you may want to write that one down. This one is given, but from this formula we can actually derive the formula to solve for the data value. All right, any questions about z-score? So although you only see this one formula, you may want to write that alternate formula as well. All right, now we're going to talk about correlation. And when you talk about correlation, we think about a scatter plot. So this kind of goes back to algebra. And a scatter plot is you just have, in a rectangular coordinate system, you have a bunch of points plotted. If the points form some kind of line, like with your visual eye, there's said to be a correlation. So a correlation exists between two variables when one of them is related to the other in some way. Now, for correlation, that doesn't mean that one causes the other. It just means that the two variables are related in some kind of way. The linear correlation coefficient R, it measures the strength of the linear relationship between the paired X and Y quantitative variables in a sample. And R is sometimes referred to as Pearson product moment correlation coefficient. All right, so let's talk about correlation. All right, correlation. All right, so we're going to take a look at 3, and these are just rough sketches. Okay. All right, so let's just say this is one of the scatter plots. All right, so just say the scatter plot looks something like that. Now you read graphs, and this goes for any graph, not necessarily the scatter plot. You read graphs from left to right just as you read numbers from left to right. So as I read this graph from left to right, it seems like these points are forming a what? Like they're forming a straight line. I can kind of draw a line through them. It won't touch every point, but those points will be in a general vicinity. So let's just say if I were to draw my line here, okay, these would be linearly related. So linear means straight line. So linearly related means that the points in your graph, they somewhat follow a straight line. If you read a graph from left to right and your line goes up, this is a positive correlation. Because as you read it from left to right, if it goes up, it's a positive correlation. Okay, so let's take a look at another scatter plot. So let's just say this one looks something like this. So here again, we're going to read this graph from left to right. And it appears that all of these points are near this line, right? So they're linearly related. But as you read the graph from left to right, the graph descends or goes down. This scatter plot has a negative correlation. And then let's take a look at a third diagram. Now we take a look at this third diagram. Now, as you read them, the line either has to go up or go down. We're not looking for any sideways lines or straight up and down. So as you look at this graph, does there appear to be a correlation between these points? No, right? Because as I read it from left to right, it's not really going up and it's not going down. They're kind of all over the place. This has no correlation. So now they mentioned that R, the correlation coefficient. So R can be in between -1 and +1. It can't be smaller than -1 and it can't be greater than +1. So what this means is that if I look at this first graph, since all of these points tend to fall on the same line, this would have a positive correlation close to 1. +1. If I look at my second graph, as I read it from left to right, it goes down. These points appear to all fit close to a line. This would have a correlation close to -1. So right here, R is close to +1. For the second one, R is close to -1. And what about the third one? Since there's no correlation at all, R is close to 0. All right, now if we take a look at, well, any questions about that correlation? This is kind of reading scatter plots going back to y is equal to mx plus b nightmare. All right, I'm going to go back to the handouts, and this is problem number 7. where it says match each scatter plot below with its best description of its correlation. So we look at the first example. Is that no correlation, negative correlation, or positive correlation? Negative, right? Because as I read it from left to right, all of these points appear to follow a downward trend. So that's going to be negative. All right, what about the second one? No correlation at all, right? Because there's no trend. And the last one is positive, right? Positive correlation. Now, there is a problem in the homework. It kind of asks you to put some numbers to them. Let me see if I can find it. Module 1. Types measurements. I believe it's in this section. Okay, it's question number 3. And this is in section 1 or module 1.8. All right. So it says match each scatter plot shown below with one of the 4 specified correlations. So notice over here now it's putting some numbers to stuff. So if we take a look at the first graph, is there a correlation? Is it positive or negative? Positive. Would it be close to positive 1 or not? It would be. So would that be A, B, C, or D? D. Right. Because the tighter the points are to the line, the closer you're going to be to 1. Right. What about the next one? It's negative. Do they appear to be tight about a line? Right, they're pretty tight, right? I can draw a line and it would almost touch all the points. It's negative, so what would be my value? Negative 0.97, which is really close to negative 1, right? What about the next one? So as you look at it, does it like appear to go, because you do have a couple of numbers left. There's a negative 0.08. So that means that if you look at a graph, it's probably going to go down, but the point's not going to be like tight about a line. And then you have 0.22, which means that if you look at it, it's probably going to look like it's going up, but they're not going to be close to a line drawn through them. So now these are kind of subjective as far as you look at them. But so let's take a look at this C. Does there appear to be an upward trend or a downward trend? I think it's like upward, right? They got these things close, but it seems like that's going up. They're not really tight together, so that would be probably A, right? And then what about the last one? I mean, as you look at it, it appears to have like a downward trend, but they're not really close together. So this should have a correlation of about B. All right. So that's problem number 3. Instead of just saying positive, negative, or no correlation, it wants you to eyeball it and put a number to it. So any questions about number 3? Now, taking a look at this last set, you'll notice that there are some ordered pair X, Y, and Z ordered pair chart, or ordered pair points, and then they're asking us to predict based off of our equation. So to explain this, I'm going into back to the handout. Just make sure I get it together. And this is problem number 8. And I do have a video doing the exact same thing I'm doing in class. I'll post it after class, but we're going to go through problem number 8. And this problem requires the use of your calculator. Right. What we're going to do is we're going to put, so before I actually read through this, this is an X and a Y ordered pair graph basically, where X is the VO2 max. That's like the oxygen. We'll kind of read through what it means in a second. And then Y is the finishing time. So what we're going to do is put this first column in as list 1. We're going to put the second column in as list 2. We're going to make the calculator give us what's called the correlation coefficient, which is the R value. Then we're going to find an equation of the regression line, and based on that equation, we're going to predict the finishing time for a runner. So now this is almost like an algebra type problem. This is as far as the algebra is going to go in this class. So the good thing is we don't have to calculate the equation by hand. We just have to know how to put it into the calculator and interpret the results. All right, so this thing reads, and I'm going to copy it over so I can write on it. All right, so the problem reads, research was conducted on the amount of oxygen runners could utilize during training, known as their VO2 max. Right, so VO2 max is just the amount of oxygen that the runners use during training. And their finishing time for a 5K race to see if there was a significant relationship between the variables. The results for 8 runners were compiled and placed in the following table. Right? So we have the oxygen level used in training, and then we have the time that that runner finished a 5K race, and his time is in minutes. All right. We want to calculate the correlation coefficient, calculate the regression equation. All right, so now this deals strictly with the calculator. So the first thing we're going to do is, and you only have to do this once, you have to turn your diagnostics on. So what that means is if the diagnostics are turned off, it won't show you the R value. So in order to turn the diagnostics on your calculator, I'm going to go into catalog. So since it's a yellow function, this is second and catalog. I'm going to scroll down to the D's, and you should see something that says diagnostic on. Now you only have to do this once. Okay. I'm going to hit enter. I'm going to hit enter again, and it says done. All right. So now you never have to do that again unless you calculate or run out of batteries or something. You got to reset it. All right, so it doesn't really appear like it's done anything, but it has, as we'll see in a second. All right, so that's the first thing. And we turn the diagnostics on in order to get this R value. All right, so I'm going to enter the data into the calculator. we're going to enter in VO2 max as X, and we're going to put that in list 1, and we're going to put the finishing time, which is the Y variable, in list 2. All right, so I'm going to put that in there. So I'm going to go into second. Well, no, not second. I'm going to hit stat. And I want to choose edit. And you should see list 1, list 2, list 3. Now, if you're not seeing list 1 and list 2, raise your hand and let me know. Make sure we're all on the same page. All right. So I want to clear out my list 1. So I'm going to go to the very top of the list. I'm going to hit clear and enter. And now I'm going to put in my values for X. And unfortunately, there is no other way to put these numbers into your calculator. You just have to punch them in, and then I would like double check them just to make sure you have the right numbers in, because a wrong number can throw off the output. And for the finishing times, I'm going to put that in list 2. And I'm just going to check. All right, so I believe I have them all in. So that's the first step, is to enter the data into the calculator. The second step is return to the home screen. So I'm going to hit second and mode, which is the quit key. The third thing we're going to do is calculate the regression equation. All right, so I want to go into I want to go into stat. Let me just go back. I want to go into stat. I want to scroll over to calculate. And the fourth option says linear regression AX plus B. I want to choose number 4. Right. And by default, it should use list 1 and list 2, but I'm going to force list 1 and list 2. So I'm going to hit second, list 1, comma, list 2. Which means you can use any list you want, any 2 lists you want. I mainly use list 1 and list 2. By default, let's say you didn't put anything, it's going to choose list 1 and list 2. Now, if you have a TI-84, are you seeing the same thing or just something different? Okay, so for the X list, yours says the same thing?
Mine says X list is 1, Y list is 2, 3.
Yeah, I don't think the frequency list should be blank.
So now we go through.
Yeah, definitely put, you have to put this one in this too.
Yeah.
And I hit calculate. Let's see. Well, you want to leave this
No frequency list.
blank. So just for the benefit of everybody. If you have a TI-84, you're going to see, what does the first one say? X list. Okay. So for X list, you're going to put list 1. For Y list, you're going to put list 2. For frequency list, it was a frequency list, right? You're going to leave that blank. Okay. But if you have a TI-83, which I doubt anybody has, this thing is so ancient. If I hit enter, you should see something that looks like this, where it gives you, now from the algebra class, when you talked about linear regression, it was y is equal to mx plus b, right? I don't know for what reason the programmers for the calculator, they chose to use an A instead of a B, but it's still the same slope intercept. It gives you the value for A. It gives you the value for B, so you can simply plug those in and get the equation. It gives you R squared, and it gives you R. So now when you turn your diagnostics on, it gives you this R and R squared. If your diagnostics are not turned on, it won't give you R and R squared. So we've already turned the diagnostics on, so you never have to do that again, unless your calculator runs out of batteries or something to that effect. So now we can pull out R. So what is R? Rounded to 3 decimals, it should be negative 0.911, right? Negative 0.911. So without like looking at the scatter plot or anything, what does this tell you? Well, it tells you since it's close to -1, that scatter plot probably looks like it's going downward, and they're probably all tight to the line. Okay. Now we can graph it. That's not a part of this, and that's like some extra steps. Okay. I'll do that later, but we just want to find R, all right, which is negative 0.911. Then it says find the equation of the regression line round each value to 2 decimals. What is the equation, the regression equation? Well, it's going to be that y is equal to ax plus b. And a is going to be what? Negative 0.46 if we round to 2 decimal places. And we're going to substitute b for 43.9. Because if we were to round to 2 decimal places, I would look at my second decimal place. If I look one number to the right, that number is higher than 5. So I have to round this 9 up, which forces this 8 to round up. So when I round to the nearest 2 decimal places, I get 43.9. Is everybody okay with that? Okay. All right. So now what's the equation? Y is equal to negative 0.46x plus 43.9. That is the regression equation. Okay, did everybody get that? All right. So the last part says predict the time in the 5K for a runner whose oxygen VO2 is 29.07. Round your answer to 2 decimal places. Okay. Now, in this regression equation, X and Y should mean something. What is X? Well, if I go back to what I put in, X is the what? Oxygen level. And Y is the what? Finishing time. So we're asked to predict the finishing time, or the Y value, for a runner whose oxygen level, or X value, is 29.07. So what should we do? We should substitute X for 29.07, right? And then that would give us the Y, or the finishing time for the runner. So like in the algebra class, it probably didn't make any sense because they give you a whole bunch of numbers in space. They tell you to find an equation that really don't mean too much because the numbers don't mean too much. But in this case, the numbers mean it's either a oxygen level or a finishing time. All right. So we're going to take this equation, and I believe it asks you for the equation separately. So I think you got to type that in. And then the last part, so this would be A, which would be negative 0.91. B is the equation, so that would be B. C says predict the run time, the finishing time. So I'm going to take the equation. And I'm going to substitute X for 29.07. So that's negative 0.46 times 29.07 plus 43.9. And I'm just going to put all of that into the calculator. Negative 0.46 times, or you could also enter in a set of parentheses, because the calculator understands that parentheses means multiplication. It's 7. 29.07. And that should give you 30.53. So runners whose oxygen level during training is 29.07, his finishing time would be about 30 minutes. All right, any questions about the last part? So like if you're looking at the homework, and this is a test question, by the way, you're going to see this on the test. All right. So if you're looking at the last part of the homework, that's basically what you're doing, putting in X, putting in Y, coming up with a model, and then sometimes you got to substitute in, okay, based on what you're trying to find. Okay, that was actually problem number 5, what we just